All right, so last one in the group, dealing with springs again. Notice in this one that we're not given a spring constant. It's also not asking us for a spring constant. So sometimes that's kind of the trap. If you don't know something, you're supposed to go get to it. Here, we don't need it. We don't want it. We don't need it. We don't have to do it. So we're not going to. What we can do is we can take advantage of the fact that springs work on a linear relationship. We have a linear constant because it was just a number. And what that means, if you have twice the force, you get twice the stretch. And if you have, one third of the stretch, you can use one third of the mass, and we can connect these things several different ways. That also means that we're a little bit more free with what we plug in. So normally our standard units, the things we'd want to use would be newtons and meters. And notice we don't have any of those in this question. But what we do have are corresponding units. So centimeters and centimeters go together with each other here. And even if I were to convert, they'd both convert with a factor of 100 because centi, like cents, means, 1/100th piece. And then grams, kilograms, what we normally want, and we know that's got something to do with 1,000 because it's got that kilo or that K involved. Technically, gravity should be here, but thankfully, all of those things are basically going to cancel each other out. What we can do is we can make a proportion, and it's great. It simplifies this so much. Whatever initial mass I have causes some change in length that, we'll determine and plug in and fix in a minute. If I converted this stuff around, then eventually I can make this into some sort of a spring constant. But I have the wrong units. It's not the goal right now. So as it turns out, whatever that number would have been ends up also being equal to the altered set of circumstances, right? So if I increase or decrease the mass, then I can find out what the change in length is. Or if I have a different change in length, then I can work backwards and find out what the other mass is. And so if we look here, that's what we're looking at. We're looking for the mass, right? So we can plug in everything else. Originally, 430 grams, which is not a force, and usually this is not okay. But because we've got different circumstances, this is actually going to cancel and work without us having to fix all the units like normal. All right, but that mass causes a change in length of 14.62 centimeters, which again would not normally be the units we'd want, but it's going to work out here. Whatever constant that would make, we don't care. Some mass later, so just M2 because I don't know what's happening, is going to cause a change in length of 27.22 centimeters. All right, so we can look here and we can simplify things slightly. So centimeters are going to cancel the centimeters. Grams are the only things left, which is good because that's what we're trying to get to. And so we can treat this like a normal proportion, cross and multiply to see what you get. I like to look at the variable first, just because it makes the equation a little bit better. I guess that's personal preference. I prefer the equation better when the variable's on the left-hand side. So 14.62 multiplied by m. I don't really know what's happening there, so I'm just sort of stuck with it for now. In the other direction, I've got 430 multiplied by 27.22, and apparently that's 11,704.6. So now that this is down to more of just an algebra sort of question, even pre-algebra and elementary school when you first learn proportions, but we just need to finish out and solve, right? So if we want to get this m, 14.62 is in the way, so we can divide that to get rid of the multiplication that's already happening. Do the same thing to both sides of the equal sign so we have symmetry and balance, and then find out that this is 800.59 grams.